Okay, so I'm going to talk through the details of the muscle spindle. So my pictures are not great. The pictures in the slide are a little bit better. So if you look at an overall muscle fiber, which is what I'm trying to show in this picture here, imagine this is your big quadricep. There are muscle fibers running the length of that big belly. These fibers are called extrafusal fibers. A fusel is like a spindle shape. So it's like a fusiform shape. So it's kind of bulbous in the middle. If you look at this picture, this little red fusel, this fusiform shape, that is the sensory organ of the muscle spindle in the belly of the muscle. There's all kinds of them there. The sensory organs of the spindle are inside of that little fusiform shape. There's going to be 5, and so this is the expanded version of that little red fusiform. Inside this spindle, there's 5 to 7 intrafusal fibers. An alpha motor neuron, the big nerve that goes from the spinal cord to innervate multiple fibers in the muscle. Motor neuron is an alpha motor neuron, and all the fibers it innervates, those are extrafusal fibers. So when that activation happens, those fibers will contract. The spindle lies in parallel with the other muscle fibers. If we look inside of the spindle, we'll have 5 to 7 fibers. Some of them are a little bulbous around their equator region, and some are straight up and down. Chains and bags. I don't care about that so much, but just you'll see it when it's drawn, both on this PowerPoint and here. Some of them, they just have a little bit different shapes. There are 2 types of sensory organs that are associated with these intrafusal fibers. Their job is to perceive change in length, and for some of them, the rate of change in length in that muscle when you're moving. Okay? So if can you toss me my collagen there? So this isn't the best example, but I'll do my best. So here's the intrafusal fibers. There are sensory organs called the 1A sensory organs, and they wrap around the equator or the central region. Whether you're a chain or a bag, they're there wrapped around the center region. It sometimes is called flower spray because it sort of splays out like a flower, but sometimes it's called annulospiral, but it's the 1A. They're wrapped around the equator, and they do 2 things. They are sensitive to change in length and rate of change in length. So if you elongate slowly, they notice that you're going slowly. If you move fast, they notice that you're going fast. So they're not only perceiving the change in length, but the rate of change in length. There's another organ called the type 2 fibers, which is sort of at the edges of the equator region. They are only sensitive to length change. So the 1As are more sensitive than the 2s, but we have both types in both types of fibers. Those sensory organs are activated when there's a change in length. So it's not a surprise if my whole extrafusal muscle fiber stretches and elongates, like you're falling asleep in class and your neck extensors are elongating. As the whole fiber elongates, the sensory organs at the middle and the edges, because the spindle is in parallel, when the whole fiber elongates, the intrafusal fibers elongate. That change in length will activate these sensory organs and send a message efferently, because they're perceiving the change, back to the spinal cord. And that message is perceived at the level of the spinal cord. And it will tell your alpha motor neuron to activate, and what you get is facilitation of that muscle. that the spindle lies within. Okay? Knee-jerk reflex, postural sway, falling asleep in class. If you elongate the muscle, the sensory organs, 1A and 2, that are at the equator or at the edges, are elongated as well. That activates those sensory organs, goes to the spinal cord, perceived, links directly to the alpha motor neuron that goes to the muscle and says contract. Spinal reflex loop. Okay? Makes sense from when we tapped. Even though you're tapping the tendon is a part of the muscle. So when you tap the tendon, you're changing the whole length of the muscle. I always thought that was kind of weird. It's called a tendon tap, but the whole muscle is changing in length because you're indenting a part of it. Okay? Yeah? When you are stretching your own muscles, if your hamstrings are tight, if you stretch your hamstrings rapidly, because these sensory organs perceive that rapid change, they may react by tightening up. Like if you do that really ballistic stretching, sometimes you go, oh, you might get that strong contraction of that muscle. That's an example of those spindles perceiving that length change, and because it was rapid, they also noticed that, hey, knock it off. Don't go so fast. You're making me facilitate. If I want to stretch my hamstrings, do I want my hamstrings activated or inhibited? I want them inhibited. I want them snoozing, like, woo, do whatever you want, right? I don't want them contracting because it's going to be harder for me to stretch it. So if you've heard anybody tell you how to stretch, or you've done any stretching yourself, do you usually go fast or slow? You go slow because you're less likely to activate these spindles because they are counterproductive when you're stretching. Because if I want to stretch that muscle and I activate the spindle, it's going to be harder for me. So I want them to be chill. It'll be better for me. Easier to stretch, more comfortable. Okay? So that's pretty straightforward, I think. If I'm looking at the slide, spindles, they lie parallel in the extrafusal fibers, check. Bag and chain, intrafusal fibers, check. The 1A annulospiral. Did I call those flower sprays before? Oh, no, I'm wrong. The flower sprays are the 2s. I'm sorry. I won't ask you that. But the 1A is the annulospiral in the equator. So 1A annulospiral sensory organ. Change in length and rate of change. The type 2s, which sort of go and look like a blossom or a flower, are at the edges. The type 2 at the border region, they're sensitive to length change, but not the rate. We can activate the spindle sensory organs by overall elongating the entire muscle. Check. Okay. But I have a problem. What do I do if the overall length of my muscle is shortening? I need these sensory organs to sort of always be in the ready position to be perceiving what's happening. And if the whole length of the muscle shortens, I end up with all of my fibers on slack. And my spindle and its intrafusal fibers are not in a ready position to perceive what's happening. So I need a fix. I need something different that will allow my spindles to still give me information when the overall length of the muscle is shortening. So if you look at this picture here, I have some purple striated hatch marks at the edges of those intrafusal fibers. You see that? This is actually striated muscle, actin and myosin. This is contractile. And it's at the edges of those intrafusal fibers. So go with me on this, okay? Here's my intrafusal fiber. If the overall length of the muscle shortens, this is going to get slack. So this equator region is not able to perceive change. But look what happens if when my overall muscle is contracting, if the two ends of the spindle, the top and bottom, contract. I go from this sloppy center to being in a ready position to perceive length change. Because both ends of those interfusal fibers have contractile muscle, when they're activated, it keeps the sensory organ in a position where it can perceive length change. These are tiny, tiny fibers. Their motor neuron is a gamma motor neuron. It's a little bitty one compared to the giant alpha motor neuron. And it's just going to these interfusal fibers in the spindle. They're there to allow my sensory organs to not only give me feedback when my overall muscle length elongates, but to create a mechanism by which they can also give me feedback when the total length shortens. And actually, they're neighbors in the spinal cord. The alpha motor neuron and the gamma motor neuron are like neighbors, right next to each other in the ventral horn, where the motor system comes from. So when alpha says, quadriceps contract, gamma says, get on board, all you little spindles, we're shortening, so we need your ends to tighten up so we can continue to have perception.
So like in very general terms, they take the slack out of the muscle spindle.
Correct. Keeping the equator or the middle portion ready to do its job. Now, back to my example, which doesn't help you if you don't have any clinical exposure, but if you know anyone who has abnormal tone, they've had a brain injury, there are normally inputs from the brain that come down and act to inhibit these gamma motor neurons. Because I don't want my spindles, I mean, I'm going to reach over and get a cup of coffee. I don't want to, have this flexion reaction. I need to have inhibition from my brain to say, okay, spindle, we know you're there. We'll use you when we need you, but we don't want you on all the time. Because if you're on all the time, every time you change the length, you're activating. That comes from inhibition from higher centers in your brain. When you have brain injury, stroke, TBI, that sort of thing, what happens is you lose that inhibition. So you see people, patients will demonstrate this abnormal activity in their muscles. They have this increased activation and tension. And when you try to move them, or they try to move, they get this response of like, don't straighten me out, I want to be contracting. Because every time you're changing their length, they've lost the inhibition from the higher centers because of the injury, and it's gamma system gone wild. So the gamma's like, we're always on. Every little elongation we're reacting to. So one of the movement problems in people with brain injuries is you see this unleashing and lack of inhibition to the gamma system to keep it in check. Neuroplasticity, you may get some recovery. You may find ways to learn to adapt. Sometimes they'll use Botox, etc. So that in your advanced neuro classes, you'll get much more detail on that. But I just want to give you the context. When you go out in OLA, you might find that you're working with some patients or participants that have abnormal neurological systems. And when you try to elongate, you might notice there is some resistance to that motion because of this abnormality. And if you do it fast, it's velocity dependent, Ashworth scale. You'll do it at a certain speed and you'll see that it acts differently because of these receptors, okay? So, what's your take home? There's a big muscle fiber, extrafusal fibers. The alpha motor neuron innervates many fibers. If you activate the alpha motor neuron, all of those extrafusal fibers will contract. Big gross muscles, large motor units. Small, fine control, fewer fibers per alpha motor neuron. We have a sensory organ in the muscle that gives us feedback about what's happening in the muscle related to length change and rate of length change. That is the muscle spindle. Inside of the spindle, 5 to 7 fibers, a couple of sensory organs. The one in the middle is sensitive to length change and rate. The other is just sensitive to length change. 2 ways to activate a muscle spindle. If I repeat things more than once, you should make a star in your notes. 2 ways to activate the muscle spindle. 1, elongate the overall length of the muscle. That will activate the spindle because the overall fibers are elongated. Number 2, when the overall length is shortening, activation of the gamma system, the gamma innervation at the edges of those interfusal fibers, will keep the equator region in the ready position to perceive that length change.